Let's have a look at a really interesting physics problem. Imagine that I have a cube, but on each of the faces, I have actually placed a resistor. If I was to apply a voltage on two of the opposing nodes, so let's say I apply some current over here and then maybe some potential difference across those two, what will the equivalent resistance be? Each of the resistors is identical. Let's call them of resistance R. This video is a collaboration with Simon Polyakov, who also runs an amazing physics channel that you should be checking out. He has some of the most interesting practical videos out there on YouTube, and he has also soldered together this exact arrangement to test our theory using an infrared camera and applying some voltage. Thank you so much for preparing this problem, Simon. I really appreciate it. So there are two different ways of approaching this problem. One of the ways would be to actually redraw the circuit and see if we can make this into something slightly more digestible. So imagine that we have some current which goes in here. The current will have three paths that it's going to take to reach to the other node. None of the paths of the current going in will actually be preferred, so by symmetry, the current will end up splitting into three equal currents. Let's try and redraw this into something more digestible. Here is the beginning of our circuit, and then we're going to split into three possible paths, i.e. this here is going to be three resistors which are simply going to be in parallel. Now, if we are here, we've got a couple of choices. So let's say we've taken this path like down here. We can either go here or we could go across this side. So that means that we're going to have two more choices, like so. Well, if we've taken this one, in order to reach the end node, we need to go through one more resistor R. If we've taken this one, we also need to go through one more resistor R as well. So we can just directly write this as that whichever way we're going to go through one of these resistors. The same will be true for any other path, and hence the symmetry argument of this circuit. For instance, let's say that if we've taken this path over here, then we could either go down here or down here, and then we could either take this one or this one to our final node. And exactly the same situation for the final path. I should have drawn this a little bit better symmetrically. It's going to be two of them like so, then another one like so, with the current from each of these combining to, well, reach the node. So this one here is the first node, this one here is the end node. Now, notice something really powerful when we're dealing with tricky circuit problems. Whenever we're redrawing, always be on the lookout for points that have the same potential difference and the same current. Can you spot any of them? Well, point over here will have the same current, which is going to be, if the initial one was I, it would be I over 3, and the same potential difference is this one, and the same potential difference is this one. So each of those are going to be exactly the same point. So that means that we can actually redraw this circuit. Additionally, all of these will have exactly the same potential difference, exactly the same current, meaning that this whole middle branch will act as a parallel arrangement. So there's going to be essentially, well, 6 of them in parallel. And as we said, we can combine those 3 points as well by simply just representing them with a single point. So all of these is that, and all of these is actually that. And then using the same argument, well, the final 3 are just simply going to be in parallel. Take a moment just to appreciate this. Imagine this part sort of coming out of the board and this part coming out of the board as well, and those two wrapping across it like this. We can see how the actual resistor cube is being built in 3D. And now the problem is quite a bit easier. It's something that we could easily see in A level now. Well, if we have, well, the equivalent resistance of just this portion will be 1/3 plus 1/3 plus 1/3 raised to the -1, which is going to be 3 over r, flipped over, which is r over 3. For this one, it will be, well, r over 6 using exactly the same arguments. And for this one here, it will also be equal to r over 3. So this means that the total resistance between this point and that point will simply be, well, r total will be r over 3 plus r over 6 plus r over 3. Let's put all of these underneath a common denominator. So what would that be? 2r over 3 plus r over 6. Multiply these by 2. What is that? 4r over 6 plus r over 6, giving us the classic answer that the total resistance of this resistor cube is actually equal to 5r over 6. Now, this is not the only way to think about this problem. If you think about this in terms of potential difference, and if you think about this in terms of current, well, initially the current is going to split into 3, right? So let's say that we had some current I that goes in. Over here, we're going to have I over 3, and then I over 3 across those 3 faces. Now, across the second face, we are going to have 2 possible options. So this one here will be, the current will then split into 2, so that will be I over 6, and this one here will also be I over 6. Now, by the time the current goes through here, we would have had a little bit more kind of flow in from the one above I over 6, which should give us I over 3 across this one. What will the potential difference between those 2 points? Let's give them some names. Between potential difference between 1 and 2. Well, the potential difference between 1 and 2, what we're looking for, is going to be equal to I times R total. And this can be actually split into the potential difference across the first cube. So let's say this one here, which will be I over 3 multiplied by one of these resistors, which is R, plus I over 6 multiplied by its resistance, R, and then across here we're going to have a current of I over 3, so that's going to be plus I over 3 multiplied by R. Okay, well, we can then simply rewrite this as 2I over 3 plus I over 6 multiplied by R, which is going to be 5 over 6, exactly like before, multiplied by I, multiplied by R. So we can see that V total will be simply equal to, well, let's say I times 5 over 6 R, but this here was true, therefore R total is equal to 5 over 6 multiplied by R. Now, this over here, though, is just theory. Did Simon's experiment confirm these results? And this is precisely why you should absolutely have a look at this next video on Simon's channel. Make sure to subscribe on both channels as well. Click over here.